All right, y'all. So 8A, that's going to deal with growth. And the growth we're going to look at is going to be linear versus exponential. Okay, let me see if I got a darker pen. All right, so I'm going to give you definitions, and then I'm going to sort of give you a little refresher on graphing. So the first, we're going to look at linear growth. Ah, that pen ain't working either, y'all. Let me get one. All right, so linear growth. So this is going to occur when a quantity, so it occurs when a quantity grows by the same absolute amount in each unit of time. All right, y'all, let me let one in. So what they mean, if my unit of time is days, then it would increase by the same amount each day. So if I had, I don't know, say we was growing something in a science class and it grew an inch daily, then each day it's going to grow by that same inch. And this is going to create, when we graph it, it's going to create a straight line. So the graphs of a linear growth, the graphs are straight lines. Okay, so sort of like y'all's pay that y'all get at work is a linear growth, because for each hour you work, you get so much money, right? You work 0 hours, you're not going to get no money. You work 1 hour and you make $10 an hour. So you work 1 hour, you made $10. You work 2 hours, you get another $10. That gives you 20. So for every hour you're working, you're gaining $10. So your pay would go up as a straight line, okay? Now we got exponential growth. So exponential growth occurs when a quantity grows by the same percentage in each unit of time. So when we was back doing those compound interest and some of those, we seen graphs that sort of came out and curved up a lot. Those were exponential graphs. So these graphs increase or decrease in sharp curves. So they're not going to be straight. So an example of exponential growth would be the COVID we're dealing with. If you remember in the very beginning, New York had a few cases in day one, but as it went, they started doubling and then doubling again and then doubling again, and those curves started shooting up. So that's what that COVID does. It grows exponentially, okay? So the way you would get exponential graphs is when you had, say, numbers and they're raised to the exponents, okay? So you start with 2 people, exponent of 1, you got 2 people, got the COVID. But if I change that to an exponent of 2, 2 times 2 is what the exponent's telling me, to multiply 2 times itself twice. Well, that turns into 4 people. All right, if you multiply it again, 4 times 2, those 4 people then turned into 8 people being sick. And then the 8 would double into a 16. 16 would double into 32. So each of my units as I grow is a percentage of the one prior to it. And I just keep doubling as I go up eventually. So if you remember on the COVID, I think New York at its peak, its doubling rate was like, what was it, like 3 to 6 days, I think. That virus kept doubling in that city from like 1,000 to 2,000 to 4,000. Okay, so exponential graphs grow up really quick or down really quick. All righty, so I'm going to refresh you on graphing real quick, and I'm just going to graph what we call quadrant 1 on the graph, just the one that you see in the real world. And I'm just going to make 10 notches out to a 10 on that. And I'm going to go up to 8 on this. But this chart right here is going to be in thousands of dollars. So that's thousands of dollars. And over here is going to be the number of games played. Okay, so let me pull this down so I can get more room on this. So what I'm going to graph, say, oh, who's a basketball player out there? Oh, someone on the Lakers. How about, okay, LeBron James. LeBron James makes $1,000 for every game he plays on that basketball court. So if we was to make us a little chart for LeBron James, the equation we would use is LeBron James's pay equals $1,000 for each game he plays. So the variable is going to be the number of games played. That's why that's my x-axis here. That's going to be the x variable. So his pay will depend on how many games he played. Okay, so if LeBron played 1 game, we would put a 1 in for the x. 1,000 times 1 would be $1,000. If he played 2 games, I would put a 2 in for the x. 1,000 times 2 would give me 2,000. All right, so let's say he played 3 games, and then that ought to give us a good idea of what's happening here. So he plays 3 games. I put a 3 in for the x. 1,000 times 3 is 3,000. But notice, for every game, it's going up by the same amount. It's going up by $1,000 in between each game, okay? So let's graph that. So over here is 1 game. At 1 game, we got 1,000. So I would go to 1 on the y-axis for my 1,000. So let's see. Go over 1 for the x, up 1 for 1,000. The next one would be 2,000. So go over to 2 on the x and up to 2,000 on the y-axis. Next would be 3,000. So go right 3 on the X's and then up to 3,000. But y'all notice what's happening. This is making a pretty straight line up through that graph. So I would know, say I didn't know and I wanted to know what he made at 7 games. So 9, 8, here's 7. So I could go up here to the 7 and I'll be at the 7 on the y-axis. So 7 games, $7,000. So once we know that line, we can start predicting all the pay he's going to make for all his games. Now, let me draw another little graph over here. Down here will be days. So I'm just going to go up to about 6 days on that. And this is going to be the number of people infected. So this is the number of people infected. And we're just going to go to 6 days on this. So the equation for that, I would start with 2 people, and it would depend on the number of days to see how many are going to get sick. And I'm doing a very minor one, okay? I'm just starting out with 2 sick people and see what happens when I double that, okay? COVID, boy, they had bigger numbers than 2 down there, okay? We had a lot of people sick, and then they all started multiplying, and then they create what they called those hot spots. So I'm going to show you how to graph these kind of equations. And I'm going to start out with 1 day, 2 day, 3 day, 4 day, and 5 days. I'll just do 5 days because that'll be plenty. So if we put a 1 in here, that gives me 2 to the first, which is 2. So anything with an exponent of 1 equals itself. All right, if I put a 2 in for that exponent, that'll give me 2 to the 2nd power. So that means multiply 2 times itself twice. So 2 times 2 is 4. So that's going to give me a 4 when the x is 2. And you ought to do exponents on this calculator, like I'm about to do 2 to the 3rd power, because that's what the 3 wants me to put in for the x. To do that, you would do, hit the 2, and then on the right side under clear, hit that caret key, we call it, the upside down V, and then put in a 3, and you'll see that 2 to the 3rd power is 8, because that's 2 times 2 times 2, which is 8. 2 to the 4th, we hit in 2 to the 4th, we get 16. And then finally, let's do 2 to the 5th. Whoops, wrong key. 2. All right, y'all, 2, cursor, what I say, 5. 2 to the 5th is 32. So notice the difference over here. This one always went up the same amount each time. It went from 100 to 2,000, 2,000 to 3,000. Next, it would have went to 4,000. Over here, these ain't going up the same amount each day. This one only went up 2, but from 4 to 8, it went up 4. From 8 to 16, it went up 8. So if you see what's happening here, these are doubling each time. They're doubling each time, okay? So that makes this graph grow a lot quicker. So watch this. Over here at 1, we were up here at 2. Over here at 2, we were up here at 4. Over here at 3, we're already up here at, let me see how many I did. So I did 10. So at 3, 8 would be right here. And watch this, at 4, this is going to be all the way up here at 16. So at 4, I'm up here at 16. So notice this graph is not what we would call a straight line. This graph is coming up, and then it's going to really start shooting up there curving, okay? My next number would have been over here at 6. This thing would have been up here at 64. So exponential graphs grow by the same rate, but it ain't the same value each time. Okay? They're being doubled, tripled, to where these ones are just growing at a nice steady rate. So let me show you some things about exponential growth. And I'm going to have to move this back up now. All right, so key facts about exponential growth. First thing, exponential growth leads to repeated doublings. Okay. So really with each doubling, you're noticing that it's actually equaling approximately the sum of all the preceding doublings. Okay. So it's sort of funny, but that's what's happening when you double it, because you're taking all those numbers from before and adding them all together. And that's really how you're going to double. Remember, I started with 2 while ago, and it doubled to the 4. Now, let's see this. Another thing about exponential growth. Exponential growth cannot continue indefinitely. Oh, let me see how to spell that. Indefinitely. Just like on that COVID, y'all, if we didn't put a stop to the rate at which it was growing, oh my God, this whole country probably would have been infected by now. Exponential growth is doubling and doubling and doubling, and we cannot continue to have those values doubling. Maybe unless it's my bank account, then I wouldn't mind it growing exponentially indefinitely. But yeah, when you're looking at viruses and sickness, you don't want it to keep repeating those doublings, okay? Because that can be hazardous. All right, so let me do a few examples, and then I wanted to go through sort of what the homework would be with you. So in the following situations, we're going to state whether the growth is linear or exponential. And then if I got another question with it, answer the associated questions. So I'm going to tell you how it's going to grow. We're going to determine if it's exponential or linear. And then we're going to see, I might ask you what happens in so many years or days or whatever, okay? So number 1, the number of students at Wilson High School. So students at Wilson High School increased by 50 in each of the past 4 years. if the population was 750, four years ago, what is it today? So we need to figure out if this is linear or exponential, and then figure out how many students we have today at, what I say this was, Wilson High School. So notice what it's saying. The students increased by 50 students in each of the past 4 years. So it's only going up 50 every year. So if it's only going up 50 every year, that means this is definitely going to be linear because it's changing the same amount. Now, since we know it's linear, we need to see how many students we have today. So wouldn't we start with our 750 students? And then I'm going to add 50 students a year. So the first year was 50, second year was 50, third year was 50, and the fourth year was 50. So to get your total, you'll start with how many students you had and then add 50 people for each year. All right, so let's see, that's what, 750, 8, 850, 9, 950. So the total students now at Wilson High School would be 950. So y'all good on that? And y'all got any questions? All right, not seeing no hands, so we get to the second one. Y'all, this one says the price of milk. So the price of milk is rising 3% a year. So rising 3% a year. If milk was $4 a year ago, what is it now? All right, so remember, when I gave you the definitions, we said that exponential graphs increase percentages, right? Has percentages of growth, which 3% is definitely a percent. So what's going to happen, it's not going to grow the same every year, because if you add 3% to a prior year, that's going to give you a bigger amount. And then the next year you would add 3% off of that new amount, which will give you a bigger amount. And eventually you'll notice that stuff will start doubling. It might take a lot of years to double, but it will have a pattern of actually starting to double, and the grass will start to shoot up pretty good. So this is definitely exponential. Now, here's the question on that one. We got to figure out how to figure out what 3% of that $4 is, because that's how much they said it grew. So you would take that 4 times 3%, but remember, you can't multiply by 3% in that form. So you're going to take that 3% and you got to turn that into a decimal. So what you would do, the decimal would technically be behind the 3, so move it left twice, and that's going to give me a 0.03. So on the calculator, you would multiply 4 times 0.03. So 4 times 0.03 is going to give me 0.12, which is basically 12 cents. But remember, we got to add that to the original $4 to get the price now. So we would have our $4 plus our 0.12. So the new price of milk is $4.12. Now that's after 1 year, so that's what they was looking for. But y'all, if I was doing this for another year, I would take my $4.12 and multiply that by the 0.03, because it's going to grow at 3% a year. And that almost is still 0.12, because that wouldn't round up really. So I'd keep that pretty much at 12 cents. So you would add that back to the original. So let's see, what would that be? 4.12 plus the 0.12, 12 cents that it rose again. That puts it at now 4.24 the year next. And then you would take that 4.24 times 0.03. Now it's almost 13 cents higher, because I would round that 7 up to a 3 on that 2, right? So eventually that milk's going to just keep getting higher, because you're going to have a higher amount that 3% is coming off of. It's not a fast grower, but it's a grower, okay? And then we noticed each year it wasn't getting the same percent, right? Went from 0.12, 0.1236 the next year, 0.1272 the next year, and so on. So let me flip this over for us and move my camera back up. So I am now going to do examples that you're going to see in the homework. So these are the homework examples. For 8A. So we're going to determine if these are linear or exponential, and then answer the questions they're asking us. So for number 1, the population of a town is increasing by 629 people per year. So the town increases by 629 people per year. So we need to know if that's linear or exponential. And then if the population is 1,300 today, what will it be in 5 years? Okay, so it increases by 629 people per year. So that means for each year, it's going up the same amount, 629. Then the next year, it's going up another 629. Then the next year, another 629. So it's going up the same amount every year. So this is going to be linear. Now we need to figure out that population in 5 years. So let's see, we said we were starting with 1,300 people. And it's increasing by 629 for 5 years. So we're going to add 629 5 times. Now I'm going to tell you a trick. If you don't want to have to write that 629 5 times just to add to the 1,300, you could take that 629 and multiply that by 5, and then add that to the 1,300. Because multiplication is just shorthand for all that adding. So you could say, hey, 629 a year times 5 years. So this part's going to add up to the 31.25.45, and then add that to my 1,300. It's going to give me 4,445 people in that town after 5 years. So y'all, these ain't bad. It's just figuring out what kind of growth you got, and then how to figure out those populations or whatever we're asking for after those years, okay? All right, so for number 2, during the worst periods of hyperinflation in a certain country, the price of food, so price of food increased at a rate of 15%. So it increased at 15% per month. So that's what hyperinflation does to you. It increases everything exponentially. So we're going to figure out if this is linear or exponential. Now, if your food bill was $80 in 1 month, what was it 3 months later? So what was it 3 months later? So remember, we're starting to talk about percentages again, and anytime I talk about percentages, I've got exponential growth. So this one is definitely going to be exponential, which means from each month, it's not going to increase at the same rate, but it will at the same percentage. So remember, to figure this out, we got to take the $80 we start with and figure out what 15% of that is. So remember, I can't do percents like this form. So we would take 15% and turn that into a 0.15. So once again, just move that decimal left twice. So let's see what 15% of 80 equals. So 80 times 0.15 is going to equal $12. Okay, so that's the first year. We went up $12. So 80 plus that 12, after 1 month, my bill went to 92. Okay, so from the first month to the second month, it went up to $92. Now, I'm doing it for 3 months, so I got to multiply the second month, which was 92. So 92 times 0.15 is going to give me $13, and basically 0.8 is 80 cents. So this almost went up 14 months. So after 1 month, now we're going to figure out 92 plus that, 13.8 is going to give me 105.8. But remember, this is from the starting month to the first month to the second month. I got to do this one more time. So I got it here, the first month, second month, now the third month. Once we figure out this decimal, we can add it back and get the final answer. So 105.8 times that 0.15 is going to give us $15.87. Add that back to the 105.8 that we started with. So I get 121.67. Now this one wants me to round to the nearest dollar. So I got 121.67 on my third month. So we're going to round to the nearest dollar. So y'all, you need to watch these, okay? First one didn't tell me nothing because it didn't end up in decimals and they knew that. This one, when it rounds into decimals, they might want you to round it to the nearest cent or the nearest dollar. This one wanted the nearest dollar. So that's in the dollar spot. So since that's a 6, I'm going to round that 121 up to a 122 final answer. So y'all look in the answer blanks because they're going to tell you how they want them answers on these problems, okay? All right, so notice, when it's linear, you're basically adding. When it's exponential, you're multiplying, okay? That's the main difference on these also, is you're repeatedly adding stuff or you're repeatedly multiplying that stuff. All right, looks like I'm on number 3. So there's only 4 of these in this homework. So that's why I decided to go through these on the lecture with you. All right, number 3 deals with computer equipment. The price of a computer component is decreasing at a rate of 11% per year. So computer component decreases at a rate of 11% per, year. That's that stuff you see in your taxes about depreciation when stuff loses value. So we're going to say if this is linear or exponential again. And then if it costs $90 today, so if the part is $90 today, what would it cost in 3 years? So what will it cost in 3 years? All right, so first of all, linear or exponential. And I'm looking at that 11%. So we're dealing with a percent again. So once again, this is definitely exponential. Now, if I want to find the value it's going to have in 3 years, remember, this says it's decreasing. So I'm not going to add that value every year. I'm going to subtract that value every year, okay? So decreasing, you'll see eventually it doubles in its decreases, okay? All right, so let me see. What are we starting with? $90. So we got to multiply that by that 11% to see how much I'm decreasing. So remember, 11% has to be in decimal form, which is 0.11. All right, so let's start out with the 90 times 0.11. That's going to give me 9.9. But remember, I'm decreasing, so I need to take that 90 I started with and subtract 9.9, which will give me 80.1. Now, that was my first year. Now I need to take the 80.1 and see what 11% of that is. So multiply that answer times 0.11, and that's going to give me 8.811. Remember, we got to subtract that from the 80 So 80.1 minus 8.811 is going to give us a new total of 71,289. Y'all, I'm just leaving all my digits till I get to the end, then I'll round this off, okay? So that was year one. Now I'm starting with the amount in year two. I got to figure out what that 11% is. So 0.11 times 71.289 is going to give me what did I got there? 7.84179. So finally, after I take that off, I will have my ending amount. So take that 71.289 minus the 7.84179 to give me a final answer of 63.44721. Now, let me see where they want me to round this off at. This one says round to the nearest cent. So remember, cents is where the second 4 is located. So since that 4 has a 7 behind it, I'm going to make this $63.45. But y'all look, remember this one said round to the nearest cent. The one I had before said round to the nearest dollar. So you got to look at that, how they want them answers in there, okay? All right, y'all, so we got one more to go. And this will be like example 4. Same thing. The value of a house is increasing by $1,600 per year. So a house value increases by $1,600 per year. If it is worth 120,000 today, so worth 120,000 today, what will it be worth in 5 years? What will it be worth in 5 years? So, and then is this linear or exponential? So I'm going to get the linear or exponential part out of the way first. So it's telling me it's going up the same amount every year by $1,600. There's no percentages involved. So since this one's telling us $1,600 per year, this is definitely going to be a linear growth. Now, they want the value in 5 years. So take that 120,000 you're starting with. And watch this. I'm going to add that to 5 times because it's 5 years. And for every year, it went up 1,600. So instead of adding 1,600 5 times, I'm just going to multiply the 1,600 times 5, and then that amount adds to the 120,000. So by hand, you would get 120,000 plus 5 times 1,600. That's going to be 8,000. So 120,000 plus 8,000, and we know that's what, 128,000. So house started at 120,000. After 5 years, it's going to be 128,000. 28,000 if it's increasing linearly, okay? So that was the main thing I wanted y'all to see, was that this house, if you was to graph it, it would start at 120,000 and then it would make a straight line as it increased, okay? While ago I had the one that depreciated and it was exponential. So on that exponential one that was decreasing, it would have went down like that and made a nice little curve. Increases go uphill curves, decreases downhill. And the same thing on these, if this house had decreased by 1,600 a year, then that graph would have actually went downhill for it decreasing. It would have started at 120,000 and then whatever 1,600 was, less than that, minus another 1,600, it would decrease linear just like it would increase, okay? So make sure if it's going up or down, and then take off the appropriate amount each year on these, and you'll be good to go. All right, so let's see. That should take care of that. So I'm going to stop this share. So let me repeat, since I had people come in late. The link in Blackboard is not working for you to upload the files in. So email me the file, and then once I grade that file, I'm going to put a grade into the MATLAB, and I'll put the grade into Blackboard, okay? So it'll actually have the grade in both places once I put them in. Okay, so let's see. That looks like everything for 8A, so I'm going to stop this recording so I can upload it for y'all to have later.